question. Okay. 1 hour, like including the question afterwards? I talked for an hour. Last question.
Yeah.
Okay.
There'll be questions.
There'll be questions during the talk, yeah.
Talking
That's.
about the talk you gave in the past.
Yeah. Yeah, well, actually, what I was trying.
Today we have from UMass lecture, and you will tell us about the distance conjecture for branes.
All right, hello everyone. Thank you for having me. Today I'm going to talk about a paper that came out in July with Ben Heidenreich and Tom Rudelius and myself, where we are introducing this new distance conjecture for branes. So just out of curiosity, how many of you all have heard of the distance conjecture? Just. Oh, okay, many people. Okay, great. I will still go over the distance conjecture in this talk. Broadly speaking, the distance conjecture says if you make a parameter very extreme in string theory, your theory will get a tower of light particles, and the lightness of these particles is related in some well-defined way to a well-defined notion of extremeness of this parameter. So that's roughly speaking the distance conjecture. And there have been some, in recent papers, some ways of making this more precise and finding precise bounds. And in this talk, I'm going to discuss a consequence of some of these recently proposed bounds, which I will call the Brane Distance Conjecture. So the structure of this talk is simple. I will just introduce to you all the Brane Distance Conjecture. I'll first tell you about the Sharpened Distance or the Distance Conjecture, and I'll discuss how it motivates this Brane Distance Conjecture. And then the second half of this talk, I will show that our conjecture is satisfied in many examples, with one exception where we weren't able to find the branes that allow for this conjecture to be satisfied. And that might suggest the existence of potential new non-BPS branes in 10-dimensional heterotic string theory. All right, so to make the distance conjecture precise, I need to talk about how parameters work in string theory. So for the class of examples I will discuss in this talk, parameters controlling things like masses of particles or tensions of branes or interaction strengths will be governed by vacuum expectation values of scalar fields. In this talk, I'll consider scalar fields that are massless and don't have potential. So I'll be assuming some sufficient amount of supersymmetry. And I'm going to call these scalar fields that I'm dealing with. There'll be typically multiple scalar fields, and they'll be labeled by I to label which scalar field I'm talking about. I'll call these scalar fields moduli. So as I said, parameters are controlled by vacuum expectation values of scalar fields called moduli. So you should think of interaction strengths, masses of particles, and tensions of branes just as functions of these scalar fields or these moduli. So a lot of work is in the Swampland program is spent on trying to find out some constraints that these functions satisfy, and just also studying the nature of these moduli themselves. If we could find some very non-trivial constraints between interaction strengths, masses of particles, and tensions of branes, maybe in the very long-term future, we might be able to constrain various parameters we observe in our universe. So there's a lot of interesting structure associated with these scalar fields. So these scalar fields, you can interpret them as being parameters of a manifold called the moduli space of string vacua. So these different phi i's are just coordinates on some manifold. So here's a cartoon manifold. This is a cartoon moduli space. So you'll have some directions where I can increase the vacuum expectation value of a scalar field and just get a different theory and just increase the VEV indefinitely. There are some scalar fields where I could change the VEV, start increasing it. And then eventually I'll go back to the same theory. these types of scalar fields where you increase the VEV more and more and then get back to the same theory, maybe with the particles shuffled around. These sorts of periodic scalar fields are called axions. So there's some interesting sorts of moduli spaces you can construct and consider in string theory and in string compactifications.
Typically, they're not manifolds though, right? There are often points where they look like orbital folds, so they're not.
Yeah, I'm sort of using maybe not the, you're right, there's sometimes singularities and manifolds isn't the right word. Maybe conifold maybe is a better word, or no, conifold isn't a better. Oh, there's a better word. Yeah, sometimes there are some singularities. Maybe I'm using a loose interpretation of the word manifold. But yeah, there are some cases where it's not strictly a manifold. So these moduli spaces, they actually have metrics, very natural metrics you can associate with them. So I said that these moduli spaces are parameterized by these scalar fields phi I. Well, these scalar fields phi I are also scalar fields. And the scalar fields, if you consider the low energy limit of your theory, these scalar fields are scalar fields in some low energy field theory action. So for instance, you have a low energy Lagrangian. Maybe right here have the Ricci scalar, but then you also have, so that the normalization of what I'm talking about is clear, but you also have these scalar fields, multiple ones labeled by I, and they typically, or I guess always, have a kinetic matrix that is a function of these scalar fields. And this kinetic matrix can be interpreted as a metric on these moduli spaces. So it has some properties that a metric should have. So for instance, it's symmetric in exchange of I and J. It has positive definiteness properties. These scalar fields aren't ghost-like, so it has the right signs of a metric. Maybe most importantly, or very importantly, if you consider some set of scalar fields phi I, but then want to consider a different set of scalar fields var phi I that are a function of the original scalar field, so you're doing a coordinate transformation on moduli space. This Gij, the one you will get for the new redefined scalar fields, will be related to the old metric with in the way that a metric for new coordinates is related to metric for old coordinates.
Can you say again how it is defined, the metric?
This Gij right here.
Yes.
So you take a low energy effective, or you consider the low energy effective action for string theory. And then you have these scalar fields. And you will find that they have a kinetic matrix. And then you have this kinetic matrix and you just define the metric as that matrix. Yes.
How do you know ahead of time, like there's no like negative eigenvalues of the matrix?
I guess that would mean that you have ghost-like scalar fields, and I think that you wouldn't have ghost-like scalar fields in the low energy effective action of string theory.
Like maybe like,
Or I know of no cases where this happens. You might run into some problems with trying to do perturbation theory or something if you had something like that happen.
It wouldn't be a stable background. You have a tachyon.
yeah, so I guess my question was much more along the lines of what Saf said, which is like if I handed you like a string solution, like how do you check such a thing?
Like, how do I check that it's a stable vacuum, or?
Yeah, or like, is this sufficient? Like I'm trying to understand like what are the necessary and sufficient parts to this?
I'd probably have to think a little bit about all the necessary conditions to get a stable vacuum. Maybe for the purposes of this talk, just suppose that I have a stable vacuum and I have this a situation like this where I have a scalar kinetic matrix that has the right properties, and these are non-ghost-like. And anyway, I'm just giving, this is just the definition if of the metric on moduli space. So anyway, we have a metric on moduli space, a natural metric, and Now we can talk about distances on moduli space, we can do integrals on moduli space, we can take derivatives of mass with respect to moduli. And now we have all these differential geometry things we can think about with these moduli spaces. So this metric on moduli space in this talk, everything I will say that requires a metric on moduli space will be in reference to this metric here. All right, so what kinds of things can we say now that we have a metric for moduli space? Well, in 2006, Ooguri and Vafa conjectured that in string theory, the moduli space will always have these spikes that go off infinitely far. So you will always have like a spike like this or a spike like that down there. All right, so roughly, maybe another way of saying this is if you have any starting point in the moduli space, you can always find another point in the moduli space that is arbitrarily far away from this starting point. So this is conjecture 1 of their paper. They had 4 conjectures, actually 5 conjectures. They had conjecture 0 in their paper. Conjecture 2 of their paper.
What's the justification of the conjecture?
It's just observed over and over again in string compactification examples. I don't think that there exists a proof for this conjecture.
Usually there's some bigger words than observed again.
Like in every single string theory example where you have moduli, it's been observed that you can.
I mean, you can have examples like weakly coupled string theory, you get a tower of strings. If you have the compactification, it could be a KK tower. So for example, every time you have the compactification, you get tower.
But there's no other words you can say other than the fact
That it's just been observed that
Yeah.
conjecture 1 seems to be satisfied in the string landscape.
Yeah. Because isn't that true that we only know how to do very small corners in string theory?
Yeah, so I guess I'm talking really about like, I guess the supersymmetric.
You want to promote this to something that's true for
Yeah,
anything.
I guess sort of the way this swampland stuff is sort of like you look at many examples and you notice stuff
But
that's
there are
true.
other things that you have some somewhat deeper sounding words you can say.
Are there deeper words I could use besides it's just
With
observed?
gravity conjecture, you have something about black hole physics.
Yeah,
you can say.
with gravity conjecture, there are all these wonderful things you can
Yeah,
say,
well,
like you can make a
but-
gauge
but-
symmetry into global symmetry.
But
or
this
stuff.
one you cannot.
But this one,
So, but this statement is that there's an infinite distance point in the moduli space?
yeah, there always exists an infinite distance point in the modular space of string theory vacua.
We don't know this is true even in field theory, I think.
Actually, in field theory, someone was telling me there are counterexamples in field theory. I'm not an expert on this, but I've heard there are counterexamples in
That
field
must
theory.
be in the swampland.
Well, I guess there you're taking sort of a strict gravitational constant goes to 0. Or Planck mass goes to infinity limit, but I have wondered whether there are different ways to view this or justify this, but
Well, that's okay.
I don't know. It's I think good and important question, but I don't know the answer. I mean,
I think it depends on what we're asking. Are we asking like if you go at infinite distance, then you find the tower, or are you asking whether the infinite distance exists? Because-
This is statement
Yeah,
out-
yeah,
this is statement
the
out-
second is that.
so I think
Is there an infinite distance?
maybe when I'm not recorded after the talk. There are things I could say about how I could use some other words about how I interpret or feel about this.
But that's not
Conjecture.
necessarily true in general,
About-
right? That you can go infinitely, like, for example, if you
Arbit-
have corrections even in n equals to 1, it could be that it becomes finite distance because of corrections.
Yeah, but
Or it
then
could
there's
be that
another
it-
limit you could take where you get arbitrarily.
So there is a limit.
Yeah, there always exists a direction you could go in.
Do we know that's always true? That's the question.
We don't know for sure. This is just, been observed. All right, so this is conjecture 1 of their paper. Conjecture 2 of their paper says that whenever you go down one of these asymptotic spikes, you'll always get a tower of light particles. You'll get, for instance, maybe KK modes or string oscillator modes. And the particles will get exponentially light with the travel. So if you travel an asymptotic distance phi in the moduli space down one of these spikes, you will always, the conjecture is, the distance conjecture posits that you will always have a tower of particles that are exponentially light in this distance phi, controlling the distance down one of these spikes. So the masses will get exponentially light as a function of the distance. And alpha is a order 1 constant if you ignore this part. Ignore what I'm sort of covering up. Ooguri and Vafa sort of just left off here and just said alpha is an order 1 constant in Planck units. And so this was 2006 where they proposed this. And for about 16 years, there were many papers that studied the distance conjecture. Many different constants were observed, like, in 10D, you would often find constants like 1 over square root of 8 or square root of 9 A's, or in 3D, often constants like 1 over square root of 2 or square root of 3/2 would appear. In all kinds of different examples, people would find these order 1 constants for these alphas. In 2022, my collaborators and I posited and argued that you will always find a tower where there's an alpha greater than or equal to 1 over square root of d minus 2, where d is the number of space-time dimensions of your theory. So in the following years, people started calling this the sharpened distance conjecture. And yeah.
So you have tower. What's the difference between the towers? Like the mass?
Like the spacing?
Yeah.
It's a good question.
I mean, for
The
example,
towers that we observe either go like, the nth mass goes like either n times this characteristic mass, or square root of n times this characteristic mass. So they're kind of like KK mode like spacing or string oscillator mode like spacing.
And only those are observed.
Only those are observed. There's I will say more about why only those are observed in a moment. There's a conjecture that implies only those two.
But that's the leading tower.
The leading tower, you're right,
You
you're right.
have sub-leading towers that are branes or something else that have different spaces.
That's a good point, yeah. So the leading order towers go this way, and then you could have branes that maybe have some other sort of
So
tower.
conjecture is that it's either fundamental string modes or KK.
Yeah, I was going to, I was gonna say that, like
Sorry.
2 minutes from now, but there is a conjecture that says that in these asymptotic limits, you either have KK modes or string oscillator modes as the leading towers. That's called the emergent string conjecture of Lee, Lerche, and Weigand. But anyway, rewinding by 2 minutes. So we propose this lower bound for this alpha. The reason why we propose this lower bound is there were multiple reasons. One is we looked at many string theory examples, and every single asymptotic limit in moduli space, which is sometimes also called infinite distance limit, we found towers of particles where alpha was always greater than or equal to 1 over square root of d minus 2. There were many cases where it's precisely equal to 1 over square root of d minus 2. Reason 2, or just an interesting thing that allowed us to originally suspect this number, is this number is special under dimensional reduction. If you have a higher dimensional theory, and you assume the sharpened distance conjecture bound in a higher dimensional theory, and you put this theory on a circle, and then consider a range of limits in the moduli space, an appropriate range of limits in the moduli space of this lower dimensional theory, you'll find that the lower dimensional theory has this bound alpha, with the lower dimensional theories d. So this is also a bound that's special under dimensional reduction. And then reason 3 that this bound was motivated, well, this was sort of elaborated on by the Harvard group, maybe 1 or 2 years after our paper, is that this, if you assume the emergent string conjecture, which says that every asymptotic limit in moduli space is either a limit where you have decompactification and then get a power of KK modes, or a limit where a fundamental string gets 0 tension, in which case the tower of like particles or string oscillator mode. What we know about string oscillator KK towers, all of the known KK towers in string oscillator modes satisfy this. There might be some sorts of KK modes when you have like decompactification of a warped compactification. that get below this bound, but we don't know of any examples.
So I'm
Yes.
confused about something very basic. So you're expressing this in terms of phi,
Yes,
and phi is some specifically chosen coordinate.
phi can be viewed as a specifically chosen coordinate. It could also be, I have a starting point A and I consider some different theory, a distance phi away from A. And then I could express that distance as a specific coordinate.
And of course, you can use various coordinates to express the infinite distance limit, right?
Yes,
But this is invariant. This expression is invariant.
It depends on the metric. So if you change the coordinates, then it changes the metric too.
but there is like a well-defined minimal distance between 2 points in moduli space.
So
The
the phi
geodesic
is
distance.
geodesic
Phi
distance.
is geodesic
Okay,
distance,
okay.
yeah.
It's not a coordinate.
Yes, phi is a geodesic distance, but you can also express the distance between 2 points as a coordinate, but
Sure.
yeah.
Makes
In
sense.
this talk, phi will refer to like this geodesic distance. And sometimes it will also be a coordinate. I'll try to be clear when it appears as a coordinate. It will appear as a coordinate on one slide in this talk. Uri, you were.
I was gonna just say that there are ways that you can follow sort of geodesics that go like this to infinity, but there's also like what usually they call like global geodesic. Like if you have a phenomenal domain, you could have gone like this to infinity, but you could have gone like this to infinity.
Yeah.
So
So
it's like global geodesic.
maybe to add what Huri's saying, you could imagine a geodesic that goes from A to B, but then ends up like sort of wrapping this like cycle. There are some conjectures about like these cycles sort of shrinking in volume. That then the difference between two different geodesic paths will be only by a finite amount. All right, so this is the Sharpened Distance Conjecture. This will be sort of fundamental to everything that comes in the next 37 minutes. So it turns out this Sharpened Distance Conjecture is not automatically preserved under dimensional reduction. So if I have a higher dimensional theory that satisfies the Sharpened Distance Conjecture, and I put this theory on a circle, the Sharpened Distance Conjecture might not be satisfied in the lower dimensional theory. There are two ways maybe to see this.
By theory, you mean string theory or gauge theory? Or
String theory, yes.
String theory.
Yeah, in this talk, I'm assuming that I'm talking about, I guess, string theories. I'm nowhere in this talk taking, I guess, a strict quantum field theory limit. I always have like finite Planck masses.
But you're talking about string theory as opposed to quantum gravity more generally.
I'm sort of focusing largely on sufficiently supersymmetric quantum field theories is what I'm saying. It would be interesting to maybe have less string theory originated or supersymmetric string theory originated statements, but I guess what I'm saying is largely based off of observations within supersymmetric string landscape. Some of these sort of dimensional reduction arguments maybe are less string theory specific, but or could apply in non-string theories. So anyway, the Sharpened Distance Conjecture is not preserved under dimensional reduction. There are several ways to see this, or several reasons it's not. First of all, in lower dimensional theories, this lower bound on alpha gets larger. Like 1 over square root of d minus 2 is a bigger number when d is smaller. So if I have a higher dimensional theory, I put this on a circle, I need the lower dimensional theory to have a larger lower bound on alpha, and I might not automatically get that from the towers of the higher dimensional theory. Another reason maybe the Sharpened Distance Conjecture isn't preserved under dimensional reduction, Sharpened Distance Conjecture is just a statement about particles getting light in asymptotic limits of moduli space. But if I put a theory on a circle, say, and I make the circle really small, generically, if I want the Sharpened Distance Conjecture to hold, I need winding modes around this circle if I make the circle really small. In some cases, I will have KK monopoles that will get light in the right way, but generically, that doesn't happen. And I need things like winding modes to get light in limits of the lower dimensional theory, where the circle's getting small. So the Sharpened Distance Conjecture fails for two reasons. The bound gets larger in lower dimensional theories, and I need stuff that gets light when I compactify on on manifolds and then make those manifolds small. I'm gonna focus on this bound on alpha being larger in smaller dimensional theories. Currently, we don't know sufficient conditions for the sharpened distance conjecture to be preserved under dimensional reduction. It seems to hold in all these different string theory examples, but we don't know like a sharp, crisp statement that is preserved automatically under dimensional reduction. In this talk, I will focus on a necessary condition. So if I want a higher dimensional theory, when I compactify it to give me the sharpened distance conjecture in the lower dimensional theory, there is a necessary condition that this higher dimensional theory must satisfy, which I will call the Brane Distance Conjecture, and which will be the focus for the rest of this talk. So the Brane Distance Conjecture is as follows. I'll give you all about 20 seconds to read this, and then I'll explain it. Okay, I'll explain this conjecture. So this is actually multiple conjectures in one. So if I have a d-dimensional theory, this is actually a collection of d-2 many conjectures, all in one. So each different conjecture is labeled by some number I'm going to call Pmax. So to find one of these conjectures, we pick Pmax to be some integer between 1 and d-2. Let's say we pick Pmax to be 3 to start with. So this conjecture says that the set of particle towers or fundamental non-particle branes with at most Pmax spacetime dimensions. Consider these objects. So Pmax is 3 in this case, so this means we're considering particles, which have 1 spacetime dimension, strings, which have 2 spacetime dimensions, and 2 branes, which have 3 spacetime dimensions. So we consider the set of particle towers and fundamental non-particle branes with at most p spacetime dimensions. If we travel an asymptotic distance, or an infinite distance limit as they're often called, we'll travel an asymptotic distance phi, then at least one of these 3 branes, or generally Pmax, many different branes, or particle towers or branes, at least one of them will have a tension that gets exponentially light with this distance. So one of the particle towers will get light with this distance, or one of the fundamental strings will get light, or one of the 2 branes will get light in the Pmax equals 3 case. But the lower bound on the tensions is now this number, 1 over square root of d minus Pmax minus 1. So what does this mean? Well, first of all, Pmax equals 1 case, that means we are only allowed to consider particle towers with the way this second sentence is worded. And this says that one of the particle towers has a mass that gets light with an alpha greater than or equal to 1 over square root of d minus 2. So this is precisely just the sharpened distance conjecture bound. But when we increase Pmax, we're allowed to consider a larger collection of objects. So not just particles, but also branes. But this conjecture is saying that when we have this larger collection of branes, we have a more difficult bound to satisfy, a larger lower bound. Roughly speaking, as I'll motivate on the next slide, this bound comes from the sharpened distance conjecture bound when we try to put this theory on a torus. The sharpened distance conjecture bound in lower dimensional theories when we compactify on a torus. So I want to point out that this bound can be really large. For instance, if you consider the Pmax equals d minus 2 case, this lower bound on alpha is just the number 1. 1 over square root of d minus 2 minus 1 turns out to be 1. And actually, that's a fun number. It's the number 1. It's dimension independent, and it's a quite large number. Actually, as we will see, in heterotic string theory, the known branes in heterotic, in the weak coupling limit of 10D heterotic string theories, the known branes don't satisfy this bound. More on that in a few minutes, but. So this bound gets larger as we go consider more and more branes or consider a larger and larger value of Pmax. So I'll give you a little bit of motivation for this statement, and then I'll show examples, but are there any questions about this statement?
Sorry, you mentioned this as a necessary condition for the sharpened distance conjecture.
It's a necessary condition.
Meaning that the original thing will imply this.
So if I have a higher dimensional theory, and I put this theory on a torus, and get a lower dimensional theory, and want the sharpened distance conjecture in the lower dimensional theory to hold, I get this constraint on the higher dimensional theory,
I see.
as I will show in this next slide.
So before you were talking about how sharpened distance conjecture may be violated, but this thing is phrasing how the violation should be avoided.
Yeah, this is sort of a necessary condition for the sharpened distance conjecture to hold in lower dimensional theory.
And is it clear
It's possible
that,
there are some flaws in the logic that when I say it's a necessary condition. But
is it clear that like, you know, as you roam around the moduli space, like you always have this type of branes, like
in this talk, I'll give you a bunch of examples where you do have these branes. That
those are all
get light
BPS
this
branes.
way. Some will be non-BPS.
Some of them are not BPS.
Yeah. In maximal supergravity, as I will show you, this is going to be satisfied by half BPS branes. Well, with one exception, but in half maximal supergravity, non-BPS branes are going to be all over the place.
I see, and you still have those branes all over the moduli.
No, not necessarily. You only have them, or you can only trust really that they exist and are well-defined when they're sufficiently long-lived. You have to be careful. It's risky talking about non-BPS branes when they have high tensions. They could be unstable. I could comment more on that in the examples that you see. So let me just, before I show you some examples, there's an argument for this from dimensional reduction, which is sort of what I said a moment ago. But if I have a higher dimensional theory with capital D space-time dimensions, and I compactify this to a lowercase d dimensional theory by putting this higher dimensional theory in a torus, this lower dimensional theory will have three different types of moduli. It'll have the moduli from the higher dimensional theory. It'll have some moduli related to the size and shape of this torus. And you will also have things like gauge fields that reduce and give you axions. Let's consider a situation where we're only varying the higher dimensional theory's moduli. So we're in this lower dimensional theory. Let's hold all of the moduli fixed except for the moduli that come from the higher dimensional theory. Well, this is a, let's travel an infinite distance limit, but only vary the higher dimensional theory's moduli. Well, this is a valid limit you can take in this lower dimensional theory, and we expect the sharpened distance conjecture to hold in these sorts of limits. So in this sorts of limits, we expect particle towers that get light with 1/square root of lowercase d minus 2. Now, you can argue, there are two different ways of arguing, or multiple different ways of arguing this. There are potential holes in this argument though, but you can argue that in these sorts of limits, where you only vary the higher dimensional theory's moduli, the particle towers you will get will have that will satisfy the sharpened distance conjecture, will actually be particle towers of the higher dimensional theory or winding modes from the higher dimensional theory. One can argue this. I could say more if people have questions about how that is argued. But if you believe this, or one can argue this, this means that the particle towers in the lower dimensional theory have masses that are proportional to the masses of particle towers or tensions of branes in the higher dimensional theory. The reason they're proportional is because we're not varying things like the shape of the torus or anything. So if you like, for instance, have a winding mode, you put string theory on a circle and you have a winding mode. But you only vary the higher dimensional theory's dilaton, then this winding mode will only depend on the, will have a mass that's proportional to the tension in the higher dimensional theory. So anyway, you can argue that the particle towers in the lower dimensional theory, in these sorts of limits, that satisfy the sharpened distance conjecture bound, have masses that are proportional to the masses and tensions of particle towers and branes in the higher dimensional theory. So with this, you can then argue that, well, if the sharpened distance conjecture is holding in the lower dimensional theory, with the lower dimensional theory sharpened distance conjecture bound, then particle towers and branes in the higher dimensional theory will get light, but with the lower dimensional theories sharpened distance conjecture bound. And what I just said is just a different wording of exactly the Brane distance conjecture. And the particular case is the P max equaling capital D minus lowercase d plus 1. So maybe to summarize what I just said, the sharpened distance conjecture bound being satisfied in these sorts of limits in the lower dimensional theory requires that the Brane distance conjecture is satisfied in the higher dimensional theory. And the bound of the Brane distance conjecture in the higher dimensional theory is coming from the sharpened distance conjecture bound in the lower dimensional theory. And we have multiple different size tori we could have compacted on. So we actually get multiple different conjectures that hold in this higher dimensional theory, because we could have compactified this higher dimensional theory on different dimensional tori and then gotten different bounds on this higher dimensional theory. So this is the rough origin of, or this is the origin of the argument for the Brane distance conjecture. Hopefully this will be clearer, and the statement of the Brane distance conjecture will be clearer with some examples. Are there any questions about this argument? Okay, let's refresh now with some examples. Before I show you these examples, I'm going to show you a nice and easy way to talk about these examples. So it's really convenient. So we've seen a lot of these e to the minus alpha phi's in this talk, where phi is the distance traveled, which sometimes you can interpret as a modulus. It's quite convenient to sort of generalize this notion of this alpha to a vector. The really convenient way to do this, or good way to do this, is you define the following vector quantity. You take minus the gradient with respect to the moduli of the logarithm of the tension of the brane. So I'll call this an alpha vector. So you can do this. This alpha vector defined this way, it points in the direction in moduli. So this is a vector field over moduli space. These alpha vectors point in the direction where, on the tangent space of moduli space, where the tension gets lightest fastest. In the case where you have a tension that is e to the minus alpha times some canonically normalized modulus phi, then this alpha vector's absolute value will be just this alpha right there. And then the alpha vector will point in the direction of increasing phi. So these alpha vectors are, as you will see, a convenient way about talking about things like the Brane distance conjecture. Just as a side comment, there are some also really fun things about these alpha vector fields in the geometry of moduli space. Quite often if you take the vector flows, or the flows of these vector fields, they're often geodesics on moduli space. And there's some remarkable relationships between alpha vectors and moduli space geometry, which I can talk about after this talk. So anyway, this is the definition of an alpha vector, minus the gradient with respect to the moduli of the logarithm of the tension. So typically moduli spaces are curved manifolds. Like the toy example you saw on a few slides back, that was not a flat flat manifold. But often you can take slices or submanifolds of moduli spaces that are flat manifolds, that are flat. So when you have a flat slice of moduli space and your collection of alpha vectors of branes and particles are constant functions or are just constants on this flat slice, then actually you can show that the Brane distance conjecture is equivalent to the condition that the convex hull of these alpha vectors contains the origin-centered ball of radius 1 over square root of d minus p max minus 1. So this sort of way of viewing this sort of convex hull statement originates in this paper by these authors, where they were thinking about the just normal distance conjecture, but it generalizes to branes, the Brane distance conjecture. Roughly speaking, the reason this works is that if I have this convex hull condition on this flat slice, and let's say I want to travel in one direction in this flat slice of moduli space, well, this convex hull condition says that I'll have at least one alpha vector whose projection along that direction is greater than or equal to this bound. And that's also that projection condition gives me a differential equation as a function of the direction traveled in that distance, in that direction. And I can integrate this differential equation, and I can just find that I thus get that tensions decay in a way that satisfies the Brane distance conjecture. So this convex hull condition, in the following slides, I'm going to test the Brane distance conjecture, and I'm going to show these tests of the Brane distance conjecture by showing you convex hulls of alpha vectors. And I'll test the Brane distance conjecture by testing whether these convex hulls contain the balls of this radius. All right, so let's first look at, yes, you have a question?
Is this, so in the convex hull, do you find like that the ball is maximally sized to hit the edges?
Very often, yes.
Okay.
Yeah.
And in cases when they don't, is there something to say? Or?
Yeah, yeah. So here's an example where precisely that happens. Yeah, I'll talk about what happens when there's saturation. Yeah, so let's take 2B string theory on a circle. So 2B string theory in 10 dimensions has two moduli. It has an axion and it has a dilaton. And I put this theory on a circle, then I get 3 moduli. I have a dilaton, I have a radion, and I have an axion. This is not a flat moduli space, but if I consider the slice of this moduli space where the axion is set to 0, so I'm now just considering the dilaton radion slice of moduli space, I guess dilaton and radion slice of moduli space where the axion is set to 0, this actually ends up being a flat slice of moduli space. So suppose I consider the dilaton radion slice of moduli space and let this direction be the direction of increasing dilaton and that direction be the direction of increasing radion. So I go that direction, the radion gets bigger, so the radius gets bigger and I decompactify. I go in that direction, it's a strong coupling limit. Or if I go in that direction, dilaton gets small, it's a weak coupling limit of string theory. So anyway, let's consider this slice of moduli space. And let's first consider the P max equals 1, Brane distance conjecture. So this means that I need the alpha vectors of particle towers to contain the ball of, in this case, radius 1 over square root of 7, 1 over square root of d minus 2. In this case, d is 9. So where are these alpha vectors? Well, I have an alpha vector right here. This is an alpha vector of a KK mode. It points exactly in the direction of the radion. So it gets light as I go up that way, the KK modes, right? In 90 Planck units, the KK modes get light in the large radius limit. Now down here, I have the winding modes of fundamental strings, and they point in this direction. So they get light when the radius of the circle gets small and the dilaton becomes very negative, right? And then down here, I have the wrapped D1 branes of 2B string theory. And sure enough, the convex hull of these 3 points does contain this ball of radius 1 over square root of 7. So in this case, the Brane distance conjecture, at least the P max equals 1 case, is satisfied and actually saturated in this direction, in this direction. So the Pmax equals 1 case is just the sharpened distance conjecture. This sort of result has been known, this sort of figure has existed since 2022. But now let's do Pmax equals 2 case. So now I need a slightly, I'm considering now alpha vectors of particle towers, but also alpha vectors of strings. And I have a slightly larger circle that needs to be enclosed. It has radius 1 over square root of 6. It's this orange circle. Now this orange circle is not enclosed in the convex hull of these particle towers. It's not enclosed in this original triangle. But now I have alpha vectors of strings. So I have a fundamental string that doesn't wrap the circle right here. Its alpha vector is here. By the way, this number 2 is because it has 2 spacetime dimensions. Number 1 is because particle towers have 1 spacetime dimensions. Anyway, I have this fundamental string there that doesn't wrap the circle, and it enlarges the convex hull. So this orange circle is enclosed in the convex hull on that side. And I have the unwrapped D1 string right here, which enlarges the convex hull in this direction here. And sure enough, this orange circle is enclosed in the convex hull with plenty of room to spare. I do Pmax equals 3. I need a slightly larger orange circle to be enclosed of radius 1 over square root of 5. And sure enough, it is enclosed in the convex hull with plenty of room to spare. I also have a wrapped D3 brane, which does nothing to the convex hull. Same story with Pmax equals 4. Slightly larger orange circle needs to be enclosed. It is enclosed with room to spare. I have a unwrapped D3 brane there that does nothing. Same thing with Pmax equals 5. I also get wrapped D5 and NS5 branes there that don't change the convex hull. Things are more interesting with Pmax equals 6. So in this case, I need a red circle of radius 1 over square root of 2 to be enclosed in the convex hull. And sure enough, it is enclosed in the convex hull, but it almost escapes here and here. So the Brane distance conjecture almost fails, comes infinitely close to failing, but it doesn't fail. So there's saturation of the Brane distance conjecture in this case. What about Pmax equals 7? So in the Pmax equals 7 case, I need that the magenta circle of radius 1 is enclosed in the convex hull of alpha vectors of these branes. And sure enough, it is. Right here, we have a wrapped D7 brane of 2B string theory, which takes care of convex hull in these directions. And here we have its S dual, which takes care of the convex hull in those directions. So there are many things to note here. There's an amazingly large amount of structure in this figure and some figures you will see in the remaining few minutes. So like these alpha vectors lie on lattices, it seems. Or you can look and see that these are a finite number of lattice points of a larger lattice. There are also some patterns, 6, 4, 2. I could have also plotted an instanton, which is here, or 1, 3, 5, 7. There's left-right symmetry coming from S duality. There's up and down symmetries sort of related to EM duality. There's all kinds of structure. One thing I want to point out is this saturation. So it's been observed that whenever the sharpened distance conjecture is satisfied, or Pmax equals 1, Brane distance conjecture is saturated, it's always in the direction of an alpha vector of a string. And sure enough, right here and right here, where we have the sharpened distance conjecture being saturated, we have an alpha vector of a string right here. Actually, that statement that you only get saturation of the sharpened distance conjecture in emergent string limits or in directions where you have an alpha vector of a string, you can show that that implies that whenever the Pmax equals D minus 3 Brane distance conjecture is saturated, so whenever, so in right here and right here, you need a alpha vector of a codimension 2 brane to be in that direction. And sure enough, there's a codimension 2 brane here, alpha vector, and a codimension 2 brane alpha vector there. And there isn't one in this direction, because remember these 6s spoil the saturation in those directions. You can also argue that this saturation condition, so the statement I last said is related to like the saturation condition of the sharpened distance conjecture in 4D. If you uplift to higher dimensional theories, you get this codimension 2 statement that I just said. We don't really know what saturation of the P max equals D minus 1, D minus 2 Brane distance conjecture means. It probably has something to do with the emergent string conjecture in string theory compactified to 3D. But that's work in progress. Also, briefly before I move on, you can also plot alpha vectors of instantons. There would be one here and here. And there is likely a not yet discovered statement about a distance conjecture for axions that could be made. Instantons that could be made. Yes?
At least in the case of 2B on tori, is there some reason why this is a conjecture rather than something you could just prove?
Well, I guess it's actually,
I mean,
it
we
is
know
a thing you can
everything
prove.
there is to know about the moduli space, we know everything there's to know about all the BPS states.
Actually, you're right.
It would be something you can't prove.
Actually, it is proved. We have proven it
Okay,
for it to be string theory in a circle.
okay, so.
So we've or on tori, we've exhaustively checked all different tori. Actually, in this exhaustive proof that we did, here are some pictures.
But
yeah.
is it a conceptual proof or is it a proof by exhaustion where you just check every case?
We did a proof by exhaustion. I don't know of a conceptual proof. A conceptual proof would be cool because perhaps then it could apply in other contexts too. So we've done similar plots for 2B string theory and higher dimensional tori. The moduli spaces get very high dimensional and I can't plot high dimensional moduli spaces, but I can just plot the dilaton volume slice of moduli space. And the convex holes look like this. So this is 8D, 70, 60, 5D, 40, and 3D. Everything I just told you about the 90 case, all of these saturation conditions, they're all satisfied. The Brane distance conjecture is satisfied for all values of P max in every single one of these cases. Often it's quite remarkable in low dimensions that if you consider the full dimensional space, these polytopes often have things like 17,000 faces or something. And they're often very high dimensional, and then you'll have saturation maybe I don't know, several thousand faces, and you can check the saturation condition in every single one of these faces, and we've done that and it works. So it's quite remarkable in those contexts. In the remaining time, let me move on to heterotic string theory. A heterotic string theory, one example. We have a little bit more in our paper, but one example. So let's put heterotic string theory on a circle. In that case, if we put heterotic string theory on a circle, there are a lot of moduli. I think there are a whole lot of axions. There are, I think, 16 axions that you'll get. You'll also have a dilaton and a radion. It's a high dimensional moduli space. I want to consider the dilaton radion slice of moduli space. So a few slides ago, I told you I'm interested in the case where the alpha vectors are constant functions of the moduli space. Well, if I consider the dilaton radion slice of moduli space, this won't always work that the alpha vectors are constant functions or constants on the dilaton radion slice, unless I have particularly well-chosen values of the axions. It turns out that I can choose, there is a particularly nice choice of axions that I'll consider. It'll be a choice where the gauge group in the lower dimensional here becomes SO16 times SO16. So let's consider this situation. Now, let's test the Brane distance conjecture in the radion dilaton slice of moduli space. Actually, now I'm going to have to deal with a lot of non-BPS branes. So, because I'll have to deal with non-BPS branes, they might not be stable when they're heavy, and I will also have to analyze the different duality frames of this theory separately. So in the dilaton, this is strange. The more is supposed to appear here. More colors. Between each one of these lines, there was supposed to be it looks like somehow this PDF remembers something about these colors. Anyway, this was supposed to be more colorful. I don't know what happened with the PDF. But anyway, you have multiple different duality frames. Each different duality frame is separated by one of these blue lines. So if I start from the perspective of putting heterotic string, SO32 string theory in a circle with these Wilson lines. So I have one duality frame, which is the large radion weak coupling frame where heterotic SO32 is the right description. I also have a T-dual description here, which is heterotic E8 times E8 string theory. I have the S-dual of heterotic SO32, which is type 1 string theory. I can take the T-dual of that, which is a theory called type 1 prime string theory. And then I also have down here M theory. So let's test the Brane distance conjecture in these different cases. So let's start with the P max equals 1 Brane distance conjecture. So I started a few minutes after 2. How long do I have? Or 1? Okay, great. So, right, so up there I have the heterotic SO32 KK mode, it's a BPS state. Down here I have the heterotic SO32 winding mode. And over here I have the type 1 prime KK mode, which is also the type 1 winding mode. And these particle towers do contain the ball of radius 1 over square root of 7. So P max equals 1 Brane distance conjecture is satisfied. For P max equals 2, I need a larger orange circle to be enclosed. I have the type or heterotic SO32 fundamental string here, which takes care of that direction. I have the type 1 unwrapped fundamental string, which is non-BPS and takes care of that direction. And I get this larger orange circle is enclosed.
I'm confused. This includes non-BPS states?
This is a non-BPS state here, and this is a non-BPS state here.
So how do you know how their mass depends on the moduli?
That's a good point. So actually, I was only going to explain this if somebody asked about this. So really only trust these alpha vectors and these states when I'm far down in that direction in moduli space. So in like the weak coupling limit of type 1 string theory, this is what the alpha vector is for the type 1 fundamental string. It just depends on the type 1 fundamental string dilaton in the usual way. And a similar thing could be said about this KK mode. So if I'm traveling in the weak coupling limit of the heterotic string theories, then you should be, as you are, rightly so, be suspicious about these alpha vectors. So actually, for these non-BPS things, only trust their values when you're traveling far in those directions. All right, P max equals 3 Brane distance conjecture, orange circles enclosed. Same with P max equals 4. Same with P max equals 5. For P max equals 6, this larger orange circle, or now red circle, is enclosed, and you have saturation here, here, and here. You don't have saturation here because of the unwrapped NS5 brane. So by the saturation condition I told you a moment ago, when we next consider codimension 2 branes, we would expect codimension 2 branes to have alpha vectors here, or there, and there. Or we are missing branes that spoil the saturation. Yes?
Okay, so you said these non-BPS states are not unstable?
When you travel in a direction where the half BPS state gets sufficiently light, then it gets arbitrarily stable. They're unstable, but when you travel, when they are like sufficiently light, their lifetime gets longer and longer, and then you can.
You're just saying that the decay channel of this non-BPS thing to decay into, say, gravitons is suppressed as you go
Yes,
near the boundary. I mean that specific
or
direction.
I think I would say that. Maybe I should think more, but yeah, I would say that, or I would say that their lifetime gets longer and longer.
What's the representation like under the SO32 for these non-BPS objects?
I don't know of a SO32 description of these non-BPS objects. I'm thinking about this duality frame by duality frame and not interpreting things outside of their duality frame or their neighboring duality frame. Since I have very little time, I want to rush through these next like 3 slides. So when we do the codimension 2 branes, well, here we find the type 1 prime B7 brane on a circle. Here we have a happy BPS state here. So this magenta circle is enclosed in the convex hull. But over here and here, the non-BPS branes that we know of in heterotic SO32 and E8 times E8 string theory are not enough for the saturation condition or the P max equals D minus 2 Brane distance conjecture. So the conundrum means that either the Brane distance conjecture is wrong or the saturation condition is wrong, which would then mean maybe the Sharpened Distance Conjecture is wrong or some step of the logic in getting the Brane distance conjecture is wrong, or there exists new branes in.
Are you including the new brains in the paper by Tachikawa?
That's a great question. I'll comment on that. Unfortunately, those branes will not be the right ones, but that's a great point. I was really thinking that they might be, but they aren't. That those would resolve things.
What tension do you need in terms of G string for new brains?
So their branes go like in string units 1 over GS squared. And I'm going to now argue that these branes that are missing, there's some reasons to suspect they should go like 1 over GS in string units, like D branes.
Well, there have been arguments that there should be such brains for a long time, based on the divergence of string perturbation theory.
Yeah, Schenker has like these, yeah, I agree. Yeah, or I guess that's just an, yeah. So, in the remaining like 2 minutes I have, it turns out there are all kinds of constraints on these alpha vectors. There's all kinds of rich structure here. In a paper from a few months ago, we found some constraints on the alpha vectors of particle towers that comes from the emergent string conjecture. Turns out particle towers, their alpha vectors have to have rules that govern their lengths and dot products between them. It turns out that these dot product rules for alpha vectors of particle towers can be uplifted to give you dot product rules and length rules of alpha vectors of branes. Here are some of them. And if you want the new branes to satisfy these dot product rules, you actually only find a finite list of possible branes that can satisfy these dot product rules. Before I spoil and say what they would have to be, I also want to point out another thing that we find quite often. If you take the alpha vector of the tensions of the mass scale associated with these branes, so the pth root of the tension of a p-1 brane, you do this for all these non-particle branes. You can plot these alpha vectors. They are these red dots here. And there's another thing in string theory called the species polytope, which is the moduli dependent cutoff on your theory. And you can take the gradient of the logarithm of this in various different directions in moduli space and take the convex hull of this. And these alpha vectors of mass scales lie on the boundary of the species polytope. Since I'm running out of time, I won't say anything about that, but I'll just say that this can be also viewed as an additional constraint. So if you want these 3 different constraints to be satisfied by these new branes, and this is the penultimate slide, you only have 2 options for these new branes. So in string units, in Planck units, either the 10D heterotic SO32 theory has a 7 brane of that tension, or the E8 times E8 theory has a 6 brane of this tension, or vice versa. And you would get the following plots of alpha vectors, and all of the rules would be satisfied. Or in string units, these new branes would have 1 over GS tensions and string units. Maybe after the talk I can say more. There might be reasons to suspect lower dimensional D-like branes in string theory as well. Or I can discuss that more. So in conclusion, the Sharpened Distance Conjecture in lower dimensions, if I have a higher dimensional theory and put it on a torus and want the lower dimensional theory to satisfy the Sharpened Distance Conjecture, I find that the higher dimensional theory, with some logic, requires, or it needs to satisfy the Brane Distance Conjecture. So to summarize, the Brane Distance Conjecture says if I travel an asymptotic limit, moduli space, an asymptotic distance phi in moduli space, I'll get among the set of particle towers or branes of at most Pmax spacetime dimensions, at least one of these will get exponentially light with this lower bound. The Brane Distance Conjecture is satisfied in many examples, with the exception of this Pmax equals d minus 2 Brane Distance Conjecture in 10D in heterotic string theory. There are some rules that govern the alpha vectors of these branes, and this work might be able to predict the existence of novel branes. So if you delete certain branes in string theory, you'll find failure. You'll find that these conjectures fail at some point. So what's really remarkable is these simple swampland conjectures holding in lower dimensional theory give you all kinds of constraints on higher dimensional theories. And maybe you would forget about certain branes in higher dimensional theories and get lower dimensional theories and see that things fail. And so these swampland conjectures, like the emergent string conjecture, give all kinds of constraints, and we don't know what all the constraints are. I just told you about one necessary constraint, and if you want something like the emergent string conjecture to hold, you need many more constraints. There are many extensions to this work. You can consider cases where alpha vectors are non-constant on moduli space. You can talk about alpha vectors in non-flat moduli spaces. You can talk about distance conjecture for instantons and axions, etc. Thank you.
I don't know if I missed it. I thought that for type 2B, you also said there was the non-BPS brane you didn't know.
Okay, for type 2B, I said that the Brane distance conjecture requires a non-BPS object. In 10D heterotic, in 10D 2B string theory, for the particle case, so P max equals 1, the only particles in 10D 2B string theory are string oscillator modes, which I think are sometimes not BPS.
I thought you wanted a higher dimensional brane.
No, actually the happy BPS branes are all sufficient.
So you're saying there are some non-BPS particles that,
There's just one small counterexample, I think, to what I'm saying, but
so you know what is there.
yeah, I know what's there.
Oh.
So this really doesn't tell us anything new about 2B string theory. Everything that we know of existing in 2B string theory is there and makes everything work. And almost everything that we need in heterotic string theory is there, except for maybe these D branes. In the examples we've searched in heterotic string theory. Oh, and then
So what if there's no supersymmetry in your star?
if there's no supersymmetry, oh, then maybe even the well, I don't know what holds when you get rid of supersymmetry.
We don't know what string theory is, no?
Yeah, where I think that it's the distance conjecture, I don't,
How do you define the moduli space metric?
yeah, one might want to say like maybe a field space metric, and there are proposals for how to measure distance is there, but that's work in progress. And
But if I break supersymmetry a little bit, what kind of corrections that you comes in?
if you break supersymmetry a little bit,
You don't have moduli anymore.
yeah, these things would get masses and potentials, and maybe there would be
You don't
some
know what to
directions
say.
in field
You
space.
don't know what to say in that case.
I don't know what to say in that case, really. Some people have thought about it, but I'm not quite sure what the status is. I think Sav has thought a little bit about,
Not so much about the distance.
not so much about the distance conjecture. Do you have a question?
Yeah, in the heterotic case, well, you said there were many axions. It's a little strange nomenclature because those scalars that come from Wilson lines. and
Wilson
dimensions
lines, yeah.
Don't really couple like axions, but anyway, they're compact scalars. But there's a huge moduli space where the gauge symmetry would be almost any rank 16 thing you want, not necessarily SO16 times SO16. Do you know that this conjecture is true more generally in that moduli space if you add these new branes that you need with tensions that go like 1/G string?
So you're asking like, for different values of the Wilson lines, like to
Yeah,
what
it's a
extent has
moduli
this sort of stuff been
space
checked?
Where you vary the Wilson lines,
Yeah,
and you really ought to be looking at this conjecture in that moduli space.
I agree, yeah,
Not at some very simple slice where you have SO16.
that's right.
16.
So we have looked to some extent for different values of the Wilson line. So like, for instance, put heterotic string theory SO32 or E8 times E8 on a circle without any Wilson lines. We haven't looked at the Brane distance conjecture, but we've looked at the Sharpened Distance Conjecture. And actually, what happens for those values of the Wilson lines, when there are no Wilson lines, alpha vectors often are not constant functions of this slice of moduli space. There's I go back a few slides. So go back here. So here, like here was heterotic SO32 on a circle with the Wilson lines that give you SO16 times SO16. What would be different if I just didn't have Wilson lines, but put heterotic SO32 string theory on a circle? Well, the duality frames would be different, like SO32 would be self-T-dual. Actually, this figure would look very similar, except now, in this one prime situation, you would have that this KK mode actually, even if you're traveling limits where the KK mode is getting light, it actually would depend on how you travel in dilaton radion space. So this blue dot here actually slides around. The half BPS states don't slide. But we've only looked at a small possible choice, small set of choices. And I don't know, I'm very interested in how the whole structure, if I consider all of the possible values of Wilson lines, how that situation works. And it hasn't been explored, or it's been barely explored. Some things can be said, but especially these non-BPS things, very little is known.
Questions? Like, thank the speaker again.